You know, from the smartphone that's probably in your hand right now, to the electric car you see on the street, it all runs on this incredible piece of engineering, the battery. But have you ever stopped to wonder how that little box of power actually works? And what does it take to build one? Well, let's dive in and unpack the unseen world of battery engineering.
All right, so here's our game plan. We're going to go on a journey from the super small to the absolutely massive. We'll start with the invisible chemical reactions, zoom out to the engineering behind a single cell, see how they're built on a global scale, meet the digital brain that keeps them safe, and finally, we'll get a sneak peek at the future of power.
Okay, first stop, inside the chemical engine. We're going right down to the atomic level to see the invisible dance that, quite literally, powers our world.
So, at the very heart of every single battery is something called a redox reaction. I know, it sounds super complex, but it's just a fancy term for a very controlled chemical reaction where electrons get passed from one material to another. Honestly, you can just think of it as a tiny, highly organized game of catch with electrons.
So how does this game of catch actually work? Well, it all happens in 4 key steps. First, one side of the battery, the anode, lets go of lithium ions and electrons. Now the electrons, they're forced to take the long way around, through your phone, through your car, and that's what powers it. Meanwhile, the little lithium ions take a shortcut, kind of like they're swimming through this special liquid called an electrolyte. And finally, on the other side, at the cathode, the ions and the electrons all meet back up. This whole dance just repeats over and over and over again every time you use your battery.
Okay, so we've got the science down, but how do we turn that into a real-world product? Well, that brings us to Section 2, engineering the perfect cell, which is all about balancing some really crucial trade-offs.
Every single battery engineer lives with this one fundamental dilemma. It's this constant tug-of-war between energy density, which is basically the size of the fuel tank, and power density, which is how fast you can empty that tank. So think of it like this. A marathon runner needs a huge fuel tank to last for hours, right? That's high energy density. But a drag racer, they need to dump all their fuel in like 6 seconds. That's high power density. You almost never get to have both, so you've got to choose what's most important for the job.
And that whole trade-off is exactly why we have so many different types of batteries. A lithium iron phosphate battery, or LFP, is super safe and lasts forever, which makes it awesome for storing energy for a whole city. Then you have nickel manganese cobalt, or NMC, which packs more of a punch. It's got that high energy density, perfect for most EVs. And the good old lead-acid battery? It's all about that huge jolt of power you need to start a car engine. See? There's no single best battery, just the best one for a specific task.
And believe it or not, the design choices don't stop there. Batteries also come in all sorts of shapes. You've got those classic cylindrical cells, kind of like you'd see in a power tool. You have rectangular or prismatic cells that are super easy to stack inside an EV. And then you have these flexible pouch cells, perfect for cramming into a sleek smartphone. The shape is always chosen to fit the job perfectly.
So, we've got a design for a single cell. Now, how in the world do we make billions of them? For that, we have to enter the world of the Gigafactory, where incredible precision is everything.
Just to give you an idea of the precision we're talking about, the coatings on the inside of the battery are applied with an accuracy measured in micrometers. That is literally thinner than a single strand of your hair. Any tiny mistake can mess up the battery's safety and how long it lasts. The scale and the precision are they're mind-boggling.
And that level of precision has to be maintained across this incredibly complex journey. It starts with mixing this chemical goo, or slurry, which gets coated onto giant rolls of foil, pressed perfectly smooth, and then cut with lasers. Then, those materials are either stacked or rolled up tight, the cell is delicately filled with that electrolyte liquid, and then, finally, it gets woken up with its first few charge cycles before being tested like crazy. It's a marathon.
But you know, a modern battery isn't just chemistry. It's also intelligent. It has a digital guardian watching over it, called the Battery Management System, or BMS for short. The BMS is basically the battery's brain. It's constantly calculating the state of charge, your fuel gauge. It's keeping an eye on the battery's long-term health, making sure all the individual cells in a pack are playing nicely together, and, most importantly, it's always watching for dangerous conditions like overheating.
And that right there brings up the single most critical job of the BMS and the entire battery design: managing heat. So what exactly do engineers do to keep these incredibly powerful devices from getting dangerously hot?
Yeah, heat is the #1 enemy of a battery's life and its safety. So to fight back, engineers have some pretty clever tricks. Simpler systems just use air cooling, with fans. More advanced systems, like what's in most EVs, use liquid cooling. They circulate fluid through these little plates that snake all around the battery cells. And the real cutting-edge stuff, that's immersion cooling, where the cells are literally dunked in a special non-conductive fluid to keep them chilly. All of this tech is absolutely incredible. But here's the crazy part. It's just the beginning. The world of battery engineering is moving at lightning speed. So, let's take a quick peek at the next generation of power. One of the most hyped-up technologies on the horizon is the solid-state battery. The idea is to replace that liquid electrolyte we talked about with a solid material. If engineers can pull it off, they think they can dramatically increase energy density. We're talking about potentially doubling how much energy can be stored in the same amount of space. That is an absolute game-changer for everything from EV range to maybe even electric airplanes.
And the promise here is just immense. It's not just about getting more energy. It's about creating batteries that are way safer because there's no flammable liquid, and they could even be cheaper and more sustainable to make in the long run. And solid-state isn't the only game in town, not by a long shot. Researchers are making huge progress with silicon anodes that can hold way more lithium. Brand new chemistries like lithium-sulfur, and even sodium-ion batteries that use cheaper, more abundant materials. And just as critical is figuring out advanced battery recycling to create a closed loop. The future is going to be incredibly diverse.
So there you have it. From that microscopic redox reaction to the Gigafactory floor and into the labs of the future, battery engineering is without a doubt one of the most critical fields of our time. It really isn't just about storing energy. It's about enabling the future of transportation, cleaning up our power grid, and connecting our entire world. So the real question isn't if better batteries are coming, it's how will we use them to build our future.